What if the future of energy doesn't come from deep beneath the earth, but from the air above it? A sheet so thin you could tear it with a breath, that can transform nitrogen and carbon dioxide into fuel, fertilizer, even building materials. Every once in a while, science reveals something that feels unfair. A discovery so elegant it borders on magic. And this might be one of them. A 2D material, only atoms thick, capable of splitting CO2 and nitrogen molecules under sunlight, two of the toughest, most stubborn molecules in the atmosphere, and rearranging them into useful compounds. Fuel, fertilizer, energy, life. But there's a story behind this discovery. A story filled with accidental breakthroughs, scientific rivalries, and one simple question. What else can this material do? It began late one night inside a materials science lab. A graduate student, let's call her Amira, was testing a newly synthesized 2D material called a metal nitride monolayer. Something was wrong. It was reacting when it shouldn't.
Why are you glowing? This isn't even a catalytic test.
She checked the readings again. The material was generating free electrons. A lot of them, just under room light. She ran the test again, but this time, with nitrogen gas flowing across it. No way, that's ammonia. She had just witnessed a molecule that normally requires extreme heat and pressure, forming at room temperature, powered only by light. That was the moment she knew. This wasn't just unusual. It was impossible. To understand why this shocked the scientific community, you need to know one thing. Nitrogen gas, the stuff that makes up 78% of our air, is locked behind one of the strongest chemical bonds in nature. Breaking that bond requires enormous energy. Today, we use the Haber-Bosch process, the industrial giant that enables global food production. But it also consumes 2% of the world's energy and produces 3% of global CO2 emissions. It's necessary, but brutal. So when Amira's sample produced ammonia under a desk lamp, scientists began asking, how can something so fragile do what factories the size of stadiums do? To understand why this shocked the scientific community, you need to know one thing. Nitrogen gas, the stuff that makes up 78% of our air, is locked behind one of the strongest chemical bonds in nature. Breaking that bond requires enormous energy. Today, we use the Haber-Bosch process, the industrial giant that enables global food production. But it also consumes 2% of the world's energy and produces 3% of global CO2 emissions. It's necessary, but brutal. So when Amira's sample produced ammonia under a desk lamp, scientists began asking, 2D materials are strange. They don't obey the usual rules of physics and chemistry. When you peel a material down to a single layer of atoms, electrons move differently. Surfaces become reactive. Quantum effects start to dominate. Sunlight interacts in bizarre ways. It turns out that some 2D metal nitrides and Mxenes create what's called a hot electron avalanche when exposed to light. A cascade of excited electrons that behave like thousands of tiny knives, slicing open nitrogen and CO2 molecules. How can something so fragile do what factories the size of stadiums do? Once nitrogen was cracked, researchers moved to CO2, a molecule just as stubborn, but with even bigger consequences. When they tested CO2 with the same 2D material, something astonishing happened. It didn't just break down the gas. Imagine every farm in the world with a small device, no bigger than a suitcase, making its own fertilizer from the atmosphere. Or rural communities generating clean fuel without pipelines, refineries, or shipping routes. Imagine carbon-neutral cars powered by methanol synthesized from CO2 absorbed directly out of the sky. Energy independence, everywhere. It assembled the carbon and hydrogen into methanol, a clean fuel. This technology doesn't mine land. It mines the atmosphere, which leads to an unsettling thought. Who owns the air? When energy becomes decentralizable, power structures shift. Entire industries can vanish in a decade. If anyone can pull nitrogen and carbon from the sky, what happens to global trade? Geopolitics? Food security? If this scales, we're looking at the most democratic energy technology ever invented. But scaling anything this powerful comes with questions. Climate strategies? It opens doors, but also Pandora's boxes. Inside the material, The reaction works like choreography. Sunlight hits the 2D sheet. Electrons surge into excited states. Nitrogen or CO2 molecules land on the surface. These electrons weaken the molecular bonds. The atoms reorganize into new compounds: ammonia, methanol, hydrogen carriers. The material doesn't get consumed. It acts like a tiny factory floor, processing molecules one by one. Scientists are now experimenting with 2D single-atom catalysts, defect-engineered lattices, ultraporous nanosheets, hybrid 2D stacks. But if a material can rewrite air chemistry, can it rewrite other chemistries too? Each new tweak reveals new reactions, some never seen before. Researchers are now asking bold questions. Could we create plastics without fossil fuels? Could we manufacture pharmaceuticals from atmospheric gases? Could we produce metals or semiconductors without mining? We're not just making chemicals. We're discovering a new way for matter to behave. Imagine future cities built on 2D material panels that produce building materials, fuels, and nutrients from the sky. Imagine spacecraft that can refuel themselves in the atmosphere of Mars. Could we create self-sustaining chemical plants powered only by sunlight? Imagine homes that literally breathe their own energy. It sounds impossible, but so did ammonia under a desk lamp. As thrilling as this sounds, there are real obstacles. Materials degrade under long exposure. Production of 2D sheets must scale by orders of magnitude. Reactor designs must become efficient and cheap. Safety standards must evolve. And then, the ethical questions. If we begin manipulating atmospheric chemistry at scale, what unintended consequences should we fear? Even good chemistry can have side effects. We're on the edge of something powerful. But power always comes with caution. But here's the truth. Whether we're ready or not, the shift has begun. Every year, new 2D materials are discovered. Each stranger, more reactive, more capable than the last. And every experiment brings us closer to a world where energy can be created anywhere. Fertilizer can be made from sunlight. CO2 becomes a raw material, not a waste product. A world where the air itself becomes a resource. If we can turn air into fuel, air into fertilizer, air into everything, then the real question isn't can we do it? It's what should we do first? And who gets to decide?